So thank you, everybody. We are going to start now the mini course of Gerhard Knieper, which is the mini course number 1. So please, Gerhard, it's up to you. Whenever you want to start, we can start.
Okay, let's see. I will. Okay. Yes. Let me first thank the organizers for inviting me to this nice event. And I think I never have been to Brazil so far. So at least now I'm somehow in an online way in Brazil. And I'm also thinking of giving me the opportunity to provide a mini course on some recent work, and I'm going to use this mini course to present recent results on manifolds without conjugate points and some coarse hyperbolicity. So I will of course introduce everything and let you know what the difficulties are here, and the hyperbolicity, which I will talk about, is really kind of very coarse. It's not weak hyperbolicity, it is much less. And under this assumption, I like to provide existence and uniqueness results of the measure of maximal entropy, which is well known in the hyperbolic framework, like another flows and some weak hyperbolic systems. And then, as if time permits, I'm interested in applying this, as usual, to say something about periodic orbits, especially about the distribution of those orbits. And then the final goal would be to get Margulis type estimate for the growth of closed geodesics. And you know all what this, at least everybody who was working with another flows knows this very nice estimate of Margulis, which he obtained in his thesis. And then later on, there were different approaches to this. And of course, here closed geodesics are meant to be closed geodesics up to homotopy, because you might have uncountably many periodic orbits, but up to what you are interested here is up to free homotopy. So all what I'm saying is based on recent joint work with Bochum, Alemanha, and Knieper. And okay, so now I have to introduce what I mean by conjugate points and coarse hyperbolicity that will come up during the talk. Yeah, question? Okay. So
no, I don't think so.
Okay, so let me start by introducing manifolds without conjugate points. It's a well-known notion, even though not well studied, because it's a complicated notion for several reasons. And the definition, of course, is very simple. It's given in terms of Riemannian geometry. So you have a complete Riemannian manifold. So completeness means that all geodesics extend to infinite time. So, and of course, if you're in a compact situation, that is already given. And no conjugate points means, so one definition is that all Jacobi fields, which are geodesic variational fields along a geodesics, which have two zeros, two different zeros, is actually a trivial Jacobi field. That means it's identically zero. Okay, so that is the usual definition. And when you look at this definition, then you have some conditions where this is really satisfied. The most famous condition where this is satisfied is condition on curvature, sectional curvature. So I don't want to, I assume that you know, have a basic course on differential geometry, and sectional curvature being non-positive implies no conjugate points, because in this case, Jacobi fields are kind of at least growing like in the flat space. So that's this comparison with flat situation. But the opposite way around is completely false, because no conjugate points does not exclude positive curvature. In fact, you can have a lot of positive curvature. So there are surfaces which can be embedded in R3, and then there's no way around positive curvature and have no conjugate points. So you have this is a much more general condition. And the difficulty is that unlike non-positive curvature, no conjugate points is by no means a local condition. You can see this will be somehow decided at infinity, so you have to travel along the full orbit to see whether there are conjugate points or not. And in non-positive curvature, you can compute the curvature locally. That's not possible with this condition. That's one thing. And the other thing is that unlike non-positive curvature, the convexity properties of the metric completely fail. And this is a very useful tool in the study of non-positive curvature. If you have this convexity properties, and that means convexity in the sense of convexity of distance functions. So if you take the distance function induced by the metric as convexity properties, or that implies convexity of geodesic walls. Then you have this nice flat strip theorem that if you have two geodesics which stay for all time in a small vicinity, then they bound a flat strip and things like that. So this is a very useful result, which is used quite a lot in geometry and dynamics. Okay, so that's the definition, and maybe the difficulties, which also somehow show that at the end there are not so many results of on manifolds without conjugate points. Nevertheless, there are some very important geometric and topological properties. The condition no conjugate points implies certain topological restrictions. For instance, if you fix a point on the manifold, you always have the exponential map. Maybe it's here, yeah. The exponential map, this can be defined on any Riemannian manifold, which is simply, if you apply the map to a vector, you take the geodesic with this initial condition as with V is this vector in the tension space, and you travel till time 1. And this somehow, this is what the exponential map is. And the exponential map, in the case of no conjugate points, they have a very special property. There's this famous old result, Kata-Hadamard result. Usually it's always stated in non-positive curvature, but that also holds no conjugate points. That this assumption of no conjugate points implies that the exponential map is a covering. And in fact, it's a universal covering, because the tension space is simply connected. It's diffeomorphic to Euclidean space. And that means the universal cover of any manifold which carries a metric without conjugate points is diffeomorphic to an Rn, where n is a dimension of n. So that's one fact. So that already excludes certain manifolds to have metrics without conjugate points. For instance, the sphere does not have it. And all this kind of manifolds which do not have universal covering diffeomorphic to Rn do not have must have conjugate points. So that's a topological restriction. And the second thing is that once you know this, you can represent your manifold in a slightly different way, namely as a quotient of this universal cover, X, simply Rn, divided by a group, gamma. This group is usually called the group of deck transformations, and it tells you how to identify points that you get at the end, the same manifold M back. And as a group, it's completely homomorphic, isomorphic to the fundamental group. Of course, the action is different. It has an action on the manifold X, but it's isomorphic to the fundamental group. And moreover, if you lift your Riemannian metric to this universal cover, this group will be act isometrically on this universal cover. And this means that the group is a subgroup of the isometry group, and not any subgroup. It's a discrete subgroup of the isometry group, so which acts fixed point free and also properly discontinuously, but I don't want to explain this here. So it has this kind of properties. And the second thing is, if you look at this lifted metric and you look at geodesics on the universal cover, then actually you can connect any pair of points by a unique geodesic, not just a geodesic that you can always do, but you can do it uniquely up to parametrizations. And that means that all geodesics in the universal cover are minimal. They minimize the distance between any 2 points, because we always have geodesic with justice, and since it's unique, it minimizes the distance between 2 points. Okay, so that's basically most important things what one can say about the geometry and say the topology of manifolds without conjugate points. Now, since this is a meeting on dynamics, the dynamical properties are of importance, and also what I want to say today in the next lectures. And there are not so many, unfortunately. And I would say, from a dynamical point of view, the most important result in this context is due to Frère and Magnier. I think they proved it in the 80s of the last century, 82, I think that's published. And the theorem tells you the following: if you have a closed Riemannian manifold, so compact without boundary, without conjugate points, and you look at the geodesic flow acting on the unit tangent bundle, then the topological entropy is actually given by a geometric quantity, and quantity from asymptotic geometry, namely it's the growth rate of balls, of geodesic balls in the universal cover, the exponential growth rate. In other words, you take log of the volume of balls of radius r divided by r, and this also converges to the topological entropy, and this links somehow the geometry to a dynamical invariant. This means also that all universal covers, that all manifolds which have the same universal cover have the same topological entropy, because you only need to compute this as a universal cover of your manifold. And of course, this in the non-positively curved setting, this has been proved is a much simpler proof due to Manning, where he used actually in the proof convexity arguments, and the Frère and Magnier they somehow overcame this difficulty and proved it in the general context of no conjugate points. And actually, there is a conjecture which has not been proved yet, and it's probably a very difficult conjecture, that if the topological entropy of a metric, of a manifold, of a closed manifold without conjugate points is 0, so if there are no hyperbolicity, then the matrix should be flat. Okay, and if you try to do this in non-positive curvature, the proof in non-positive curvature works. So it's true in non-positive curvature, and it's also true for surfaces, because in surfaces you use the uniformization. Either you are, in the case of a sphere, you can exclude because they have conjugate points. A torus, if it has no conjugate points, that's an old result of Hopf that tells you that the metric has to be flat. And in higher genus, you have a background metric of negative curvature, and this implies that the topological entropy is positive. So if one does not add any further condition to this, to those manifolds, it's clear, at least to my knowledge, I have no idea how to go on and get further results. So they're very, very difficult if you don't want to add certain extra conditions. And that's what I mean by coarse hyperbolicity. So we want to add further conditions to get the results which we want to prove. But of course, there should be natural conditions. And the conditions which we add are at the beginning actually only 2 conditions. Namely, one condition is, which we want to add, that the manifold should carry a second metric, and the second metric should have negative curvature. So that's, I call condition H1. So it's one of my hyperbolicity condition, the existence of a metric with negative curvature.
Sorry, may I ask a question?
Sure, go ahead.
Yeah. No, please, who proved that conjecture by Magne? That is just listed a little bit above.
The conjecture is not proved yet. It's only proved in non-positive curvature. You are asking whether this, this, I should say, this is open. Whether the conjecture is completely open.
No, because my confusion was that just below it's written true if k less or equal to 0 or dimension of m equal to 2.
Yeah, that is. And this uses.
The full generality is open. Is this what you are saying?
Full generality, it's open.
Okay, thanks.
The non-positive curvature, if you, I mean, the proof is not that difficult because you use really convexity of spheres or Hall spheres. And then you have some rigidity and you get, I mean, this is a simple proof. So this is, if you, okay, so this is not, I'm
okay,
not
thank you.
Prove this at first, so in a non-positively curved world. Okay, so in other words, if you want to get results, we should add certain conditions. One condition is this background metric of negative curvature. Of course, if you have a surface of genus at least 2, you always have this second metric of negative curvature. And then comes a condition. I'm not sure of if we really need this, but this makes life a little bit easier for, and you will see why. And that second condition is the following. If you fix any 2 geodesics in the universal cover, or geodesic rays, I should say, and which have a common initial point, and are not and are different, then they diverge. The distance of the 2 geodesics will go to infinity as t tends to infinity. So this, of course, is again true, or easy to see in non-positive curvature because geodesics diverge as fast as in the flat case, so you have at least a kind of a linear divergence. But in no conjugate points, this is not clear. Even so, this divergence condition has been proved in dimension 2 by Leon Green. So this is Leon Green proved it in the I think in the 50s already, true in dimension 2. This is this divergent condition is true in dimension 2, which means that H1 and H2 is true for all surfaces without conjugate points and genus at least 2. So in this paper, Leon Green claimed to be able to prove it also in higher dimensions, but the proof contained some gaps, which I think has been noticed first by Eberlein. So when he read this, Patrick Eberlein, he realized that there was a gap in this proof, and so this is not. It might be true that this is always the case, but there is no proof yet of this property. So that is a condition which you might be able to remove later on, but we did it for convenience. We added this condition. So why?
Excuse me, Gerhard.
Yeah.
So do you usually require both hypotheses?
Yeah. I'm depends. But for the final results, I acquire this.
Okay.
Not when I say certain things, they have the certain properties are also hold also without just with one property, but for when I state final results, I will need this property.
Okay,
At least the way we prove things. I mean, maybe one can avoid this, and that is not clear yet. So why are the partitions helpful, especially H1? H1 is helpful because of a very nice and old result of Morse. So the Morse actually proved this result, which I'm stating now already in the 20s of the last century. It's an amazing paper of Morse. And he, modern language, I would call it Morse shadowing lemma. Of course, Morse never talked about shadowing, but it's what it is. It's a kind of a coarse shadowing lemma. And actually, Morse proved it in dimension 2, but it holds also in higher dimensions. And higher dimensions, the proof of what I'm saying now was given by Klingenberg. So what does this theorem tell? So okay, so you have a metric. Actually, when I state this now, I even don't need no conjugate points. So you will start with any closed Riemannian manifolds which carries such a background metric of negative curvature. And then you have geodesics on the universal cover of the metric G and of the metric G naught. So, and you can compare them. And the assertion is that those type of both geodesics, both classes stay in bounded distance. In other words, if there is a universal constant depending only on the chosen metric, the background metric and the metric G, which was completely arbitrary, such that if you take now two geodesics, one in the metric G tilde, which was the metric which you lifted to the universal cover, and one with respect to G naught tilde, the negatively curved metric, and you assume that the endpoints of the geodesics are the same. So you have, it's not, you have this of the endpoints of the geodesics should be the same. Then if you add that Z is a minimal, a distance preserving, distance realizing geodesic, as I said, in no conjugate points it's automatic. So if this is a minimal geodesic, then the distance, the Hausdorff distance of the two geodesics is bounded by this universal constant R, depending only on G naught and G. So that's a universal bound. And why can that ever be true? The reason is that hyperbolicity punishes you if you travel far away from your original geodesic. That's basically the idea. You would not realize the distance if you travel too far away from your optimal and of this original geodesic, and that's what the way the proof goes. So it's a kind of a hyperbolicity. It's but it's not the constant which you have here might be very large. So, but it's a finite constant. That's a nice thing. So okay, and that's this condition we use to get compactification of the universal cover. It's kind of a geometric dynamical compactification, which at the end will be very useful to get, has been used quite a lot to get dynamical or geometric results. And how do you define? It's a very standard way of compactifying the space X. What you do is you look at all in the universal cover, you look at all unit speed geodesic rays. So with respect to your metric G, not, and now I assume no conjugate points. Now I assume no conjugate points, and you take all geodesic arrays and you set up an equivalence relation on the set of geodesic rays, and you say that two are equivalent if the distance of the two geodesics, not the half, the real distance is bounded. So there's a bounded function. The universe is a sum bound. And it's easy to see that this will define equivalence relation on all geodesic rays. It's clear by the triangle inequality. You see that this is an equivalence relation, and you define an equivalence class as a point at infinity. So that's a nice notation to say C infinity is not a point, it's a kind of equivalence class of all geodesic rays, which are equivalent to the geodesic Z in the sense which I explained above. So you take all, this defines you a point. And then all points together form the so-called ideal boundary of X. Okay, now what do you do? Of course, if you leave it like that, you cannot do very much with this. You need a topology on the boundary. And before that, I want to say that each point at infinity, and for each point at infinity, this is what this lemma, which I'm now explaining, and each point in the universal cover, there exists a unique geodesic ray with initial point P, such that it belongs to the equivalence class C. So in other words, you can realize, you can take a representative for each point at infinity. You find a representative geodesic which starts as a prescribed point P. So, and here to prove this, at least that this really exists, such a geodesic makes use of the Morse shattering, namely roughly speaking, the proof goes as follows. You realize that this result is true in negative curvature, and that means you find such a geodesic connecting P and the point at infinity. And then you use Morse shattering to get this geodesic C. So that would give you a realization of each equivalence class by a prescribed geodesic C starting at P. And now the second condition H2 showed that this is unique, because if you would have another geodesic starting at P with the same point at infinity, by definition that would mean that they have bounded distance, but I excluded that that there are two geodesics which or two geodesic rays which have bounded distance, because H2 tells you that all geodesics starting at a point diverge. So that means you can realize each point at infinity by a unique geodesic starting at a prescribed point P. So now it's clear what to do, how to get the topology on this boundary. Namely, you fix such a point, and now you can define a map which associates to each unit vector, or each unit vector. So SPX denotes a set of unit vectors with foot point P. You take all these vectors and you associate to them the point at infinity by looking at the geodesic with initial condition V and take its point at infinity. And this defines by the lemma before a bijection. So you can realize all points at infinity by vectors in a unit tangent, in unit vectors with the same foot point P. And now the standard thing, you equip the boundary with a topology such that this map is a homeomorphism. And then the boundary is nothing else topologically like an n-1 dimensional sphere if the dimension of your manifold was n. So it's an n-dimensional sphere. And then, of course, here I fix this point P, but you could fix another point, and the claim that is that this would not, of course, change a little bit the realization, but not the topology. So if you take another point, this will give you the same sphere topologically. So you have topology is independent of P. And now you want to unify both topologies. So you have already a topology on the manifold X, and now you have a topology on the boundary. And now you equip both sets together with a topology such that the map which I'm writing down here is a map which you fix a point P as before, and now you take all unit tension vectors of lengths smaller than 1. So this here, yeah. And you map that into this X bar, which should be then the compactification of the manifold X, by defining the map as follows. In the first situation, if the vector is smaller than 1, you use the exponential map, and the vector, the exponential map of V divided by 1 minus V in the norm, and if V approaches 1 in the norm, then this explodes, and if V is 1, you just take the definition before, you take its point at infinity with or you take the geodesic with initial vector V, and you take CV infinity. And now you demand that this map phi P will be a homeomorphism. And again, this fixes now a topology on the full space. And by doing this, X bar will be a closed N ball, will be homeomorphic to a closed N ball in Rn. So that means your universal cover is now topologically a very nice space. It's just a closed N ball, and that this is a compact space will be important in what I'm going to say later on.
Excuse me, Gerhard.
Yeah.
Is it difficult to check that this topology in the boundary is independent of the base point P?
You have to work a little bit, but it's not too difficult. It's a little exercise. I think maybe in the literature which I gave, for instance, my handbook article, there's a proof of that. I mean, this is
okay. Thanks.
This is okay. Now, another consequence of the Morse shattering is that if you have any two points at infinity, you can somehow connect them by a geodesic. So there's always a geodesic Z, which has the property that the C infinity is eta, and if you run backwards, C minus infinity psi. So you can connect any 2 points by a geodesic, but this is usually not unique. So in non-positive curvature, it's not unique, and this is a difficulty. So it's a negative curvature. You would have a new unique connection, but in our setting, you might have many connections. So that's one thing. Okay, so that's the topology and which you introduce, and the compactification of the universal cover. And now there are important functions associated to this boundary structure, and they are usually called Boseman functions. So if you fix a point at infinity, you can define a Boseman function. What I'm saying here is not usually a Boseman function has only one variable, but let me introduce a slightly more general version. So this point at infinity introduces a function which is defined on the product of the universal cover into the reals by doing the following. So you fix, okay, so maybe you fix a point Z, which you eventually will send to infinity, and you take the distance function of the distance of another point Q from Z, and you subtract the distance of a second point from P from Z. So that means that, so if you have, maybe I draw this here, you have here you have here a point Z, and then you have a point P, and then you have a point Q. So you take Q.
It's this. Not visible what you're writing.
What?
It's not visible what you're writing.
It's not difficult, no.
Visible.
It's not visible. Ah, this is not visible, I'm sorry.
Maybe you can just change the color.
Ah, okay. The color, no problem. Okay, maybe I draw it here. So you have here a point Q. Here you have a point P. And you look at the distance of these 2 points from a third point Z. So this is this. Now you take the distance from P to Z, from Q to Z, and subtract the distance from here to here. By triangle inequality, this expression is always smaller than the distance between Q and P. And what you do now is you move with your point Z to a point to infinity. And this limit actually exists. And and this limit exists, and the definition actually of this function b psi. So it's a function which depends on q and p, and this is the definition. And the function by itself is always, or the norm of this function is always bounded by the distance of the points q and p. Okay, so I will explain a little bit more about this function because it's quite important. So it has several properties. One is immediately, it comes just from the definition of this function. If you take three different points, you fix a point at infinity, but you take three different points, then you have this kind of co-cycle property. So if you take the Boseman function on P1, P2, and at P2, P3, then it's the same as the Boseman function from between P1 and P3. Okay, what is the geometric meaning of this? If before you go to the limit, if you take a set in a finite point, then the levels clearly of this function are spheres with center z. So if you fix a level, that means you look at all points which such that bzqp is constant, then and p is also a fixed point, then this will be spheres with center z. And if the center moves to infinity, then the levels are so-called Horus spheres. And I draw this picture, which is somehow well known in negative curvature, but it's also true now in this situation. The level, for instance, if you take as a level the level 0, and then you get the function is clearly 0 if q is equal to p, then you will get a Horus sphere passing through this point p and based at this point at infinity. Okay, that are the Horus spheres. And if you fix this normalization, p is a kind of a normalization, you fix this p, then you get what is called a Boseman function. And the Boseman function has another property. If you take now one of those geodesics, so maybe I draw here another geodesic, which connects this point. I said you can connect any 2 points, one in the boundary and one in the manifold by a unique geodesic. So I take this C x psi. Then if you travel here along this geodesic and you plug it into the Boseman function, then the Boseman function just is linear on this geodesic. That in other words, that it's equal to t, at t equal to 0, you're on a 0 level, and then you move up and down. And that means geometrically, you can think of a Boseman function as the signed distance from this fixed Horus sphere. So if you take now any point q, here it measures the distance from this Horus sphere through p. And if you're outside of the Horus sphere, it's plus. And if you're inside, if you're here, it would be positive, and here it's minus negative. So it's kind of a distance, kind of a distance function, not to a point, but to a set, and the set is the Horus sphere. So that's what the Boseman function is. And if you can prove some regularity of this Boseman function, it's always a Z11 function. It's differentiable, and it has Lipschitz gradient. And the gradient, of course, as usual, distance function, it has gradient 1. It's the norm of the gradient is equal to 1. So that's so it's a kind of a distance function, but somehow assigned distance to some object, which are Hall spheres. So it measures this kind of distance to Hall spheres. Okay. Now, let's see, maybe I have 3 minutes. What do you do with this compactification? So my goal is somehow to, at the end, to say something about measures, especially measures of maximal entropy. And I use, for that, I use measures at infinity. So now you have your interior of the universal cover and you have the boundary. And there's a very nice and well-known way of introducing measures. And this goes back to Patterson, though he was the first to introduce this in a very special case, namely if you are in surfaces of constant curvature, even non-compact constant curvature surfaces, and Sullivan somehow extended it and he used for many, many different things. And what I want to do is to use it for dynamical purposes. And so I will introduce this measure in our framework, namely to have a remaining manifold. So condition is again as before. You have a remaining manifold without conjugate points with these two conditions, H1, H2. H1, existence of a metric of negative curvature. H2 is this divergence property. And then one introduces certain series which reflect somehow the group action gamma on the universal cover that are called Poincaré series. And the series depend on two parameters on the universal cover and on a real parameter on R. And it's formally given by a sum over all group elements. And what do you sum? You sum e to the minus s times the distance of p from the orbit gamma. Where gamma is any deck transformation group element, and q is a fixed point. And this measures already somehow a distribution. It's kind of a distribution of the gamma orbit with respect to this point q seen from p, how this develops. And now, of course, the question is where does the series converge? And this is not so difficult to see. If you remember that the topological entropy is given by the volume growth, actually a slightly more general statement is that this topological entropy is also given by the volume growth of geodesic spheres. Instead of taking balls, you take spheres. I mean, at the end, most of the mass of a ball is concentrated on the boundary, so you can also take geodesic spheres. If you use this, then one can prove, and this I will actually do this, maybe not today, to show that the series converges if S is large, and large means bigger than the topological entropy, like this H. And it diverges if S is smaller than this number. And okay, do I have more time or I'm not sure.
Actually, you have minus 4 minutes.
Oh, I'm sorry. But I started 5 minutes later, yeah. But okay, so I will explain this tomorrow. Then I will somehow say what the properties of this measure are, and maybe also tomorrow we'll see how this can be used to construct an invariant measure for the geodesic flow, which then we want to compute the entropy of this measure, so that it has maximal entropy. And of course, this is what I plan to do tomorrow. Okay, then I will stop here and start again with Petersen-Sarel measure tomorrow.
Okay, thank you, Gerhard. Let's thank Gerhard. We have time for some questions. The first one is in the chat. Andrei Gogolev, he asked if the C11 regularity is only in dimension 2.
No.
So it's in any dimension.
It's in any dimension. It uses somehow a kind of Arcilla Ascoli. I actually proved it in my thesis many years ago. The C11. And of course, there is a much more general statement, which is due to Albert Fatih. So he looked at Hamilton-Jacobi equations. So this distance function is somehow, if you look at distance one functions and you take the gradient, the gradient are usually always geodesic flow lines. And if you look in this more Hamiltonian worlds, then you realize that this kind of regularity is true for much more general situations. But I proved it in the 80s just for in this setting, no conjugate points. So you find also either, at least in the handbook, my handbook article. It's not a dimension 2 condition. Another point, of course, the boundary, you have to be careful of the boundary. The boundary is only a topological boundary. There is no smoothness. And then, at least in negative structure, the boundary has, the structure has a C1 structure. And that was actually used, even though Hopf never used it, but in the Hopf argument, the C1, if it's a C1 structure, that somehow is in correspondence to the fact that the foliation, stable and unstable foliation, has a C1 structure. That was used by Hopf to prove ergodicity, and maybe it has also a Hölder structure. But in this setting, I'm pretty sure it's not better than continuous. So the structure, the topology, which I introduced, has no kind of smoothness condition. So if you ask how does this Husemann function depend on the point at infinity, then this is just continuous, I would say.
We have more questions. Pablo raised his hand, his virtual hand.
Okay.
Thank you. I have two questions, or maybe they are short. The first is maybe I apologize if this is very simple, but I'm.
No, it's okay.
When you define the ideal boundary, in general, I knew it for negative curvature. And then if you look at the fundamental group of the manifolds, right, you have a conversion action. But here, you may have non-uniqueness on the points. So I guess that you also get an action in the boundary of the fundamental group of your manifold, but maybe
no, for this I don't need. Not of course, if the fundamental group at the end acts on the boundary, that's clear.
Yes.
So you have an action, but for the construction of the boundary, I did not use. I'm using maybe the background structure of negative curvature, but I'm not using the group action.
Sure, no, but I mean, so you also this action that you get in the boundary, is it simple or is it known?
Maybe at the end. Okay, in our I didn't say anything about the action.
Yes,
but at the end, it's a minimal action.
It's a minimal action. I see.
It's a minimal action. So that's what we are going to use actually.
Okay, I see. And okay, thank you. And the other one is about the Mayen's conjecture. Is it if there is any advances, for example, in dimension 3 for three-dimensional manifold?
Not that I know of. Maybe, okay. But this is okay. I mean, it's related to other questions. So if the topological entropy is 0, that means also that the volume growth is sub-exponential. And then what's also not known, if it's sub-exponential, it's actually already polynomial. So that's, it could be something in between, but nobody knows. It's an old problem. I mean, if you have you can also think of the fundamental group as a group, and you take the usual word metric and ask yourself what kind of growth do you have with respect to the word metric, and then it's not known if there is some intermediate growth. Of course.
Oh, I see. It's like the Grigorchuk.
Open question. I mean, there's of course some examples of groups. Of discrete groups where you have intermediate growth, but these groups are as groups are finitely generated, but also finitely presented. So there are only finite many relations, and it's finitely generated. And for such groups, it's not known if there are groups intermediate growth. So that would mean that topological entropy being 0 would already mean that the fundamental group would, if that would be true, then it would polynomial growth. And if you have polynomial growth, you are in a much better situation, because then you probably can show that the group is almost nilpotent. And then you are quite close to the torus case. So that would be the idea. Go to the torus. I mean, at the end, show that this manifold, if the topological entropy is 0, is kind of a covering of a torus. And then you can use Burago-Ivanov. They proved if a torus has no conjugate points, that's the old Hopf problem. They solved it in the 90s. That under this condition, the metric is flat. So a torus without conjugate points is flat. That's easy to prove in dimension 2. It's kind of with the help of the Riccardi equation, but the higher dimension, the proof does not work. And this uses an Burago-Ivanov. So that's somehow the idea, but as I said, there are many open intermediate problems. If you go this way, then maybe as a group theoretic, what kind of groups are actually acting on such? What kind of properties do they have? And that.
Thanks a lot. It was very, very clear. Thank you.
It's a completely open thing. I mean, this is difficult. I mean, if I'm okay, so my thesis is from '85. So, and this thesis I already considered no conjugate points. And since that time, there are many open problems which I already saw, and at that stage of my career at the beginning, which are not solved till now. I mean, so no, there are not so many results in this framework. That's a problem with this. It's a nice condition, but it's a difficult condition.
Okay, I believe we have time for one more quick question. If Ali wants to make it, please do.
Yes. Okay, so very quick question.
Yeah.
What is the regularity of these objects? For instance, Boozman function or its gradient, or even Patterson-Sullivan measures, with respect to the metric G. So beginning from the Morse lemma, we have everything topological. So my question is, do we know any stability results, anything when you perturb the measure? The metric.
The metric.
Yeah.
Perturb the metric, what is the regularity in the perturbation of the metric? First of all, that depends a bit on the perturbation. So the no conjugate points, this condition on the set of all metrics is not an open condition, obviously.
Okay.
it's a closed condition.
Mhm.
And then actually that's I think that was proved by Ruhr, but that if you have a Riemannian metric without conjugate points and assume that you have a full neighborhood of metrics without conjugate points around this, then the original metric was actually Anosov.
Okay.
There's another characterization of Anosov geodesic flow. I didn't mention this, but that Klingenberg and Manier, they proved that, Manier a more general statement, but they proved that if you have an Anosov geodesic flow, it has no conjugate points. So they all have no conjugate points.
Okay.
So, and that excludes, of course, possibilities to have geodesic Anosov flows. And that means now if you take now a metric, it should be on the boundary of the metrics without conjugate. If it's not Anosov, it should be somehow on the kind of on the boundary. And then if you take a perturbation of the metric, it's likely that you will see conjugate points. And then it's not so clear how to define the Boseman function. That might not exist for this, at least not globally. Maybe in certain directions the Boseman function exists, but maybe not in all directions. So that it's not so clear whether this is at the end then meaningful to study this.
Thank you.
Okay, so I believe it's time to thank Gerhard again. It was nice